Welcome to Lecture 5. This will be our final lecture on the geometry of space. Today we were talking about lines, planes, and projections. First, let's talk about lines. To describe a line in three-dimensional space, we need two things. We need a point, which the line passes through. We'll call this point P0. Here it is in the picture. And we need a vector which is parallel to the line. We'll call the vector V. The vector gives the direction of the line. Then any other point on the line, let's say the point P, must be equal to the point P0 plus some multiple of V. So the definition is that the line L, passing through the point P0, parallel to the vector V, has the vector equation R is equal to R0 plus TV, where R is the vector from 0 to P, and R0 is the vector from the origin to P0. And T is any number between minus infinity and infinity. This equation is equivalent to xyz is equal to the point x0, y0, z0, that's the point we know is on the line, plus t multiplied by v1, v2, v3. So it's plus t multiplied by the vector. Or we could split this up into three different equations. I could write x is x0 plus t v1, I could write y is y0 plus t v2, and z is equal to z0 plus t v3. These three equations are called the parametric equations for this line, the line passing through the point P0 parallel to the vector V. For example, find parametric equations for the line passing through the point -2, 0, 4, parallel to the vector 2i plus 4j minus 2k. First, we take the P0 numbers, that's -2, 0, and 4. -2, we put in the first equation. 0, we're going to put in the second equation, because the second equation we can think of as 0 plus 4t. And the third number, the 4, we're going to put that in the third equation. Then we look at the vector v. Here the numbers are 2, 4, and -2. 2 goes in the first equation, it's the number in front of t. The 4 goes into the second equation. Again, it's the number in front of the t. And the -2 is the number that we put in the third equation in front of the t. So the first equation is -2 plus 2t. The second equation is 0 plus 4t. We can just write that as 4t. And the third equation is z is equal to 4 minus 2t. We're just taking the numbers in the question and then understanding where do we put them. Here is a picture of this line. The line x is equal to -3 plus 2t, y is equal to 4t, and z is equal to 4 minus 2t looks like this. It passes through the point -2, 0, 4 when t is equal to 0. When t is equal to a half, we move to here. When t is equal to 1, we're here. When t is equal to 3 over 2, we're here. We could also use negative t. When t is equal to minus 1, we're about here. I've also drawn the vector v on this graph, on this picture. You can see that the line is parallel to the vector v. Another question. Find parametric equations for the line passing through the point P and the point Q. Now, to answer this, we need two things. We need a point on the line. That's easy. We already have 2 points on the line. We could choose either one we want. And we need a vector which is parallel to the line. So for the point on the line, we have a choice. We could either choose P or we could choose Q, and it really doesn't matter. I choose to use P. We need a vector which is parallel to the line. We could use the vector from P to Q. That must be parallel to the line. As soon as we know these two things, we can do what we did in the previous example. We can write down the 3 equations. We just look at the x equation first of all. The minus 3 comes from the point on the line, and the plus 4 comes from the vector. And then we look at the y equation. 2 comes from the point, and the minus 3 comes from the vector, and so on. Now, up to now, we've been letting t be any number between minus infinity and infinity, but that doesn't have to be the case. We might restrict t to be between 2 numbers, between a number a and a number b. That would be a line segment. For example, parameterize the line segment joining the point P and the point Q. These are the same points P and Q from the previous example. So we already know x, y, z equations. What we need to know is what values of t are we going to be allowing. Now note that if t is equal to 0, then we get the point P. We get minus 3 plus 0, 2 minus 0, and minus 3 plus 0. So we're at P. And note that if we let t equal to 1, then we have minus 3 plus 4, or 1, 2 minus 3, that's minus 1, and minus 3 plus 7, that's 4. If we let t equal to 1, then we get to the point Q. So the answer is, for this line segment, we let t be any number between 0 and 1. Why is it 0 and 1? Because we use the vector pq to decide on our parameterized equations, so parametric equations. So, of course, it's going to be 0 and 1. Here is a picture of this line segment. The line segment joins P and Q. We have the point P when t is equal to 0, and we have the point Q when t is equal to 1. Let's look at, actually, let's skip this example. Next, I want to talk about the distance from a point to a line. What is the distance between the point S and the line L? And to be more precise, I'm looking at the shortest possible distance from the point S to the line L. So I'm looking for the length of the line when I have a right angle just here, when I have a 90-degree angle. Now, we can use trigonometry. We can see from this picture that the distance d must be the same as the norm of the vector ps multiplied by sine theta. But remember, we were talking about the cross product last week. Remember that we had the cross product definition. PS cross V is the norm of PS, norm of V sine theta n, where n is a unit vector. And that's almost the same as what we have at the top. There's norm of PS, sine theta, sine theta. N, we don't need to worry about this because when we take the norm of n is just going to be 1. So that's going to disappear when we take the norm. Divide both sides by norm of V and then take the norm. We can see that they are the same. The distance from the point to the line is the same as the norm of PS cross V divided by the norm of V. This is the formula that we're going to be using. So, for example, find the distance from the point 115 to the line x is equal to 1 plus t, y is equal to 3 minus t, and z is equal to 2t. We need a point on this line, and we need a vector which is parallel to this line. So we're going to be doing what we did before, but in reverse. For the point on the line, we look at the first numbers. That's 1, 3, and here it would be 0, because this is 0 plus 2t. For the vector, we look at the numbers in front of the t. So that's 1, minus 1, and 2. So we can say that the line passes through the point 1, 3, 0, and in the direction v is equal to I minus j plus 2k. Now we have the information that we need. Now we can start calculating the distance. We need the vector from P to S. We do S minus P. You can check that that's minus 2j plus 5k. We need the cross product of PS and V. Again, I leave this for you to check. Check the calculation. This must be I plus 5j plus 2k. And then our formula says that the distance from the point to the line is the norm of PS cross V divided by the norm of V. And again, I leave this for you to check. You can check that this is square root of 5. So let me just repeat the key points here. We need a point on the line, so we look at the first numbers, 1, 3, and 0. We need a vector on the line. For a vector, we look at the second numbers, 1, minus 1, and 2. And then after that, it's just using the formula. I want to talk about intersecting lines next. This, if you're following along with Thomas's calculus textbook, this is not in the subject material, that it's hidden away in the exercises. We say that two lines intersect at a point P if and only if the point P lies on both lines. So, for example, do the following two lines intersect? And if the answer is yes, where do they intersect? The first line is x is equal to 7 minus t, y is equal to 3 plus 3t, and z is equal to 2t. Because I've already used the letter t for the first line, I need to use a different letter for the second line. And I'm choosing to use the letter s for the second line. The second line is x is equal to minus 1 plus 2s, y is equal to 3s, z is equal to 1 plus s. The two lines are going to intersect at a point if and only if we can find s and t where these three equations are all true. We need 7 minus t to be the same as minus 1 plus 2s. And we need to have that 3 plus 3t is equal to 3s. And we need to have that 2t is equal to 1 plus s. So the question is, can we find s and t so that all three of these equations are true at the same time? What can we say from this? We can take the first equation and see that t must be 8 minus 2s. The second equation simplifies that s is equal to t plus 1. We'll look at these two to start with. So for the time being, let's forget about the third equation. We'll come back to the third equation later. The first equation says that t is equal to 8 minus 2s. And if we put this into the second equation, s is equal to t plus 1. That's 8 minus 2s plus 1, or 9 minus 2s. Rearrange this, we can see that we must have s is equal to 3 and t is equal to 2. So to recap, if we use s is equal to 3 and t is equal to 2, then we know that the first equation and the second equation are true. And then comes the time to look at the third equation. Is the third equation also true? We need to check this. We need to check, does s equal to 3 and t equal to 2 also work for the third equation? We can calculate 2t is equal to 4, and we can calculate that 1 plus s is also equal to 4. So the answer is yes. The third equation is also true. Using s equal to 3 and t equal to 2 means that all three equations are true at the same time. So that means that the two lines do intersect. They intersect when s is 3 and t equal to 2. So they intersect when x is 5, y is equal to 9, and z is equal to 4. Let's do another example. Two more lines. Do these lines intersect? And if the answer is yes, where do they intersect? That's the same as saying, can we find numbers s and t such that all three of these equations are true? This time, let's start with the second equation. The second equation looks the easiest. The second equation tells us that s must be equal to t. Next, let's go to the first equation. Let's put s equal to t into the first equation and see what we get. The first equation then becomes 2 plus t is equal to 2t, which then tells us that we would need to have t is equal to 2. And then, of course, s is equal to 2. What about the third equation? Is the third equation also going to be true? The third equation then becomes, using s equal to t, 2 plus 2t is equal to 0, which implies that we would need to have t is equal to minus 2. This means that it's not possible to find a number s and a number t such that all three equations are true at the same time. That means that the two lines do not intersect. The next idea is the distance between two lines. Here, there's three cases we should think about. Either the two lines intersect, that's the easiest one. If they intersect, then the distance between them must be 0. Or we might have two parallel lines. Parallel means that vector 1 must be equal to some constant multiplied by vector 2. And there's actually a little bit of information missing here. It says for some k in the real numbers, and actually we need to have k is not equal to 0. Or the third case is that we have lines which do not intersect and are skew. In other words, v1 is not equal to some number multiplied by v2. We'll talk about these three cases separately. The first one, the easiest one, clearly the distance between intersecting lines is 0. So that's easy. Let's move on to the next one. What about parallel lines? We have parallel lines if we have parallel vectors. And if you remember from last week, we have parallel vectors when their cross product is equal to the 0 vector. Look at this picture. The distance between the two lines, that's the number d, is the same as the distance from the point P2 and line L1. But we already know how to find the distance between a point and a line. So we'll just use the same formula again. Slightly modified, the distance between two parallel lines is the norm of the vector P1, P2, cross the vector V1, divided by the norm of the vector V1. And of course, we don't have to use the vector V1 if we wanted to. We could use the vector V2, as long as we use the same vector on the top and on the bottom. We could use V2 on the top and V2 on the bottom if we wanted to. We'll do an example using this later. Perhaps. The third case is the idea of the case of skew lines. These are lines which do not intersect and they are not parallel. So V1 cross V2 is not the 0 vector. How can we find the distance d in this picture? Now notice that there's two right angles in this picture. The line from Q1 to Q2 is orthogonal to L1 and it's orthogonal to L2. How can we get a vector which is orthogonal to V1 and is orthogonal to V2? We can take V1 cross V2. Then the vector n in this picture, if I draw it, would be like this. The vector n would be parallel to the line from Q1 to Q2. So this distance, that's the norm of the vector from Q1 to Q2. Q1 to Q2 is just the projection of the vector P1, P2 onto n. It's the part of the vector from P1 to P2 which points in the same direction as the vector n. And we have a formula for the projection of a vector onto a vector from last week. We'll use that here. And if we take the norm of this formula, we get the absolute value of P1, P2 dot n divided by the norm of n. But n is just V1 cross V2. So the formula that we're going to be using is the distance between skew lines is the absolute value of P1, P2 dot V1 cross V2 divided by the norm of V1 cross V2. So let's recap. Case 1, the distance between intersecting lines is 0. The distance between parallel lines, that's lines where V1 cross V2 is the 0 vector, is given by this formula. And the distance between skew lines, that's lines which do not intersect and which have V1 cross V2 is not the 0 vector, is given by this formula. We're going to do an example. We're going to do an example now on the next slide. First, we need to understand, do we have intersecting lines or parallel lines or skew lines? And that will tell us which formula that we want to use. After we know which formula that we want to use, it's a case of putting the information into the formula and getting the number. Find the distance between the following two lines. Line 1 is x is equal to 0, y is equal to minus t, z is equal to t. Line 2 is x is equal to 1 plus 2s, y is equal to s, and z is equal to minus 3s. We need a point on each line, and we need vectors which are parallel to these lines. First, look at line 1. To get a point, we could just set t equal to 0. Then we would get x is 0, y is 0, z is 0. The point 0, 0, 0 is on line 1. To get a vector, which is parallel to line 1, we look at the numbers in front of the t terms. So 0, minus 1, 1. Move on to line 2. To find a point on line 2, we're going to replace s by 0. We get 1 plus 0, 0, and 0. The point 1, 0, 0 is on line 2. To find a vector which is parallel to line 2, we look at the numbers in front of the s terms. So 2, 1, minus 3. And then I'm going to tell you that these two lines do not intersect. That would normally be the first thing we would check, but I'm just going to tell you that these two lines do not intersect. The next step is to calculate V1 cross V2. And I'll leave it for you to check that the answer is 2i plus 2j plus 2k. That's not the 0 vector. Because V1 cross V2 is not the 0 vector, we know that these two lines must be skew lines. So that tells us which formula then it's just a case of putting the information we have into the formula. Because P1, P2 is just I. On the top we have the absolute value of I dot 2i plus 2j plus 2k. And on the bottom we have the norm of 2i plus 2j plus 2k. I leave it for you to check that when we calculate all of these things and simplify, we get 1 divided by the square root of 3. Our second chapter for this week is about planes. To describe a plane in space, we need two things. We need a point on the plane and we need a vector which is perpendicular to the plane. This vector n, which is perpendicular to the plane, is said to be normal to the plane. Now, if P is any other point on the plane, then the vector from P0 to P is contained inside the plane. That means that the angle between that vector and n must be 90 degrees. These two vectors must be orthogonal. In other words, n dot, the vector from P0 to P, must be equal to 0. And this is our definition of the vector equation for a plane. In terms of coordinates, this is the same as a, x minus x0 plus b, y minus y0 plus c, z minus z0 is equal to 0. And we can rearrange that to get the standard equation. The standard equation for a plane is ax plus by plus cz is equal to some number d. So, for example, find an equation for the plane passing through the point minus 3, 0, 7, normal to n is equal to 5i plus 2j minus k. We need to put the numbers into the standard formula and then rearrange. First, let's do n. Here, a is equal to 5, b is equal to 2, and c is equal to minus 1. We also need to put the numbers from P0 into the equation. X0 is minus 3, Y0 is 0, and Z0 is 7. So we have 5 multiplied x minus 3 plus 2 multiplied by y minus 0 plus minus 1 multiplied by z minus 7 is equal to 0. If we rearrange this and simplify, we get the standard equation. 5x plus 2y minus z is equal to minus 22. Now, before I go on, for the normal vector, the numbers are 5, 2, and minus 1. From that, we know that the answer is going to be 5x plus 2y minus z is equal to something. This whole calculation was to find the something. This whole calculation was to find that the something is minus 22. Let me repeat that. The vector ai plus bj plus ck is normal to the plane ax plus by plus cz is equal to d. So, for example, if I gave you the plane x plus 2y plus 3z is equal to 4, and I asked you to find a vector which is normal to this plane, you would just look at the numbers in front of x, y, and z. The numbers are 1, 2, and 3. So the normal vector must be I plus 2j plus 3k. It is that easy. Next example. Find an equation for the plane containing the points 0, 0, 1, 2, 0, 0, and 0, 3, 0. We need a point on the plane. That's easy. We've got 3 of them. We could choose any one of these that we wanted to. And we need a vector which is normal to the plane. We know that the vectors EF and EG lie in the plane. How can we find a vector which is orthogonal to EF and orthogonal to EG? We could just take that cross product. The normal vector that we're going to be using is going to be EF cross EG. So I've written first we need a vector which is normal to the plane. We're going to take EF cross EG, and I'm going to leave it for you to check that when we calculate this, we get 3i plus 2j plus 6k. We need a point in the plane to call P0. We could choose E, or we could choose F, or we could choose G. It really doesn't matter. We'll get the same answer in the end. I'm going to choose the point E. I'm going to choose the point 0, 0, 1. Now that we have our normal vector and we have our point, it's just a case of putting them into the equation and rearranging to find the answer. I'll leave this for you to check later. My next idea is the idea of lines of intersection. Two planes are parallel if the normal vectors are parallel. In other words, if n1 is some number multiplied by n2. A real number k which is not 0. That's one possibility. The other possibility is that these two planes intersect in a line. They intersect if n1 is not parallel to n2, if n1 is not a number multiplied by n2. And the line that they intersect in is called the line of intersection. How can we find a vector which is parallel to the line of intersection? Well, the green vector must be orthogonal to n1 and it must be orthogonal to n2. How do we find a vector which is orthogonal to both n1 and n2? We can take the cross product of n1 and n2. So anytime we want a vector which is parallel to the line of intersection, we'll just take n1 cross n2. Here's an example. Find a vector parallel to the line of intersection of the planes 3x minus 6y minus 2z is equal to 15 and 2x plus y minus 2z is equal to 5. We need the two normal vectors. We can just write that down straight away because we'll just look at the numbers in the equations. The first plane, it's 3x minus 6y minus 2. The numbers are 3, minus 6, and minus 2. So the first normal vector is going to be 3i minus 6j minus 2k. And for the second plane, we do the same thing. The numbers are 2, 1, and minus 2. So the second normal vector is going to be 2i plus j minus 2k. Then all we need to do is we need to calculate the cross product of these two vectors to get our answer. A vector parallel to the line of intersection is 14i plus 2j plus 15k. Let's move on. Next, I want to imagine we have a line and a plane. Suppose the plane looks like this. And let's suppose we have a line which somehow somewhere intersects the plane. Find the point where this line intersects this plane. What we're going to do is we're going to start with the equation for the plane. We start with 3x plus 2y plus 6z is equal to 6. But we have a formula for x. X is 8 over 3 plus 2d. I'm going to put that here. We have a formula for y. Y is minus 2t. I'm going to put that in instead of y. And we have a formula for z. Z is 1 plus t. Instead of z, I'm going to be writing 1 plus t. So here we are. 3 multiplied by 8 plus 3 plus 2t, plus 2 multiplied by minus 2t, plus 6 multiplied by 1 plus t is equal to 6. Let's multiply these out. And then let's simplify. This equation simplifies to t is equal to minus 1. So the line intersects the plane at the point on the line when t is equal to minus 1. With this information, we can write down the point of intersection. The point of intersection is the point x, y, z when t is equal to minus 1. So we take our equations at the top. 8 over 3 plus 2t, y is equal to minus 2t, z is equal to 1 plus t, and we replace t by minus 1, and we find that the point is 2 over 3, 2, 0. The distance from a point to a plane. Again, the smallest possible distance. So we're looking for the distance d when there's a 90-degree angle just here. Let's look at the right-hand picture now. From the right-hand picture, we can see that the distance d is the same as the length of the vector projection of PS onto n. So the distance from a point to the plane is the same as the norm of the projection of PS onto n. We have a formula for the projection of a vector onto a vector from last week. So the distance from a point S to a plane with normal n containing the point P must be the absolute value of PS dot n divided by norm of n. This is our formula. Let's do an example using this formula. Find the distance from the point 1, 2, 3 to the plane x plus 2y plus 3z is equal to 4. First, we need a point in the plane. We need a point x, y, z which satisfies the plane equation. And of course, there's infinitely many points in the plane. So it's infinitely many possible numbers that we could use for this point. How can we choose one? We can make it easier for ourselves by insisting that 2 of the numbers are 0. Choose 2 of the numbers, choose x and y, choose x and z, or choose y and z. It doesn't matter which 2 you use. I'm going to choose y is 0, and I'm going to choose z is 0. Choose 2 of these letters, it doesn't matter which 2, and put them equal to 0. So our plane equation then becomes x plus 0 plus 0 is equal to 4. X is equal to 4. Okay. We can use the point 4, 0, 0. This is a trick you can use anytime you want to find a point on the plane. Choose 2 of the coordinates to be equal to 0, doesn't matter which 2 you choose, and then calculate the other coordinates. I could have chosen that x is 0 and z is 0, and then my equation would be 2y is equal to 4, so I would choose y equal to 2. The point 0, 2, 0 is also on the plane. It also satisfies the plane equation. We need a vector which is normal to the plane. That's very easy. The numbers in the plane equation are 1, 2, 3, so clearly the normal vector would be I plus 2j plus 3k. At this point, we have all of the information that we need. The formula is at the top in the yellow box. We know P, we know S, and we know N. So then it's just a case of doing the calculation. We can calculate that PS is minus 3i plus 2j plus 3k. We can do the dot product with n, and then we can divide by the norm of n. And I will leave the calculation for you to check. When you come back to this, when you rewatch the video or when you read the lecture notes, please check the details and please check that the distance from this point to this plane is 10 divided by the square root of 14. If you have a copy of Thomas's calculus, have a look at example 11 in the textbook as well. Let's talk about the angle between two planes. Looking at this picture, we can see that there's actually two angles that we could be interested in. We could be interested in the angle theta, or we could be interested in the angle 180 degrees minus theta. And actually, the one we want is whichever one is smaller. We either want the angle between N1 and N2, or we want 180 degrees minus this angle, whichever one is smaller. The angle between two planes is defined to be equal to whichever of the following angles is the smaller angle. Either the angle between N1 and N2, or 180 degrees minus the angle between N1 and N2. This is because the angle between two planes we want to be always between 0 degrees and 90 degrees. Here's two planes. Find the angle between these two planes. We need the two normal vectors. That's easy to write down. And we want to calculate the angle between these two normal vectors. We have our formula for the angle between two vectors is inverse cosine of n1 dot n2 divided by norm of n1, norm of n2. You can check that if we put the numbers in here, what we get is inverse cosine of minus 4 over 21. And if we then have access to a calculator, we can calculate that this is approximately 101 degrees. But we want an angle that's between 0 and 90 degrees, and 101 degrees is bigger than 90 degrees. So what we're going to do is we're going to do 180 degrees minus this angle. The angle between these two planes is approximately 79 degrees. And that brings us to the third and final chapter of today's lesson. We're going to be talking about projections. Before I start this chapter, would you like a 10-minute break, or shall I just continue? Okay, looks like the majority would like a 10-minute break. So I'm going to start again in 10 minutes. And now let's continue. Chapter 16 is about projections. We've already talked about the projection of a vector onto a vector, but we can do more projections. Last week, we defined the projection of a vector u onto a vector v to be u dot v divided by norm of v squared multiplied by v. The next type of projection I want to talk about is the projection of a vector onto a line. Look at the line L, the blue line. I want to project the red vector onto the blue line. In other words, I want to squash the red vector down onto the blue line, or we can think about this another way. If we imagine that there is a sun up at the top, we could be looking at the shadow of the red vector on the blue line. The projection of the vector u onto the line L is just the same as the projection of the vector u onto the vector v. So, for example, find the projection of the vector u onto this line. First, we need a vector v, which is parallel to a line. We can read that off straight away, just looking at the parametric equations for the line. It must be 2i minus j minus 4k. And then the projection of the vector u onto the line L is the same as the projection of the u onto the vector v. So u dot v divided by norm of v squared multiplied by v. Put the numbers in and simplify. I'll leave this for you to check. When you have a moment to rewatch this video or to read the lecture notes, check the details, check that I haven't made a mistake here. It should be minus 2/3 I plus 1/3 j plus 4/3 k. Next type of projection, the projection of a vector onto a plane. Let me show you the picture first. I want to project this red vector onto the plane. So either we squash down, use a large force to squash the vector u down onto the plane, or think about this another way, we can imagine that there's a sun up here shining down, and we're looking for the shadow of the red vector onto the blue plane. We're trying to find the green vector. What we do know is the orange vector. We know that because the orange vector is the projection of u onto n. So we want the green vector which completes the triangle. In other words, the projection of the vector u onto the plane is just going to be u minus the projection of u onto the normal vector n. Let's do an example. Find the projection of the vector I plus 2j plus 3k onto the plane 3x minus y plus 2z is equal to 7. We know the normal vector straight away. We'll just read the numbers off the plane equation. The numbers are 3, minus 1, and 2, so the normal vector must be 3i minus j plus 2k. We can calculate the projection of u onto the normal vector. Please check that it's 3 over 2i minus 1 over 2j plus k. And then the answer to this question is going to be u minus that vector. So again, please check it. I'll leave it for you to check that the projection of u onto a plane, that's u minus the projection of u onto n, is minus half I plus 5 over 2j plus 2k. The projection of a point onto a plane. I want to take the point P and I want to project it onto the plane. So either I push from up here and I squash the point P down onto the plane, or we can imagine the sun is at the top and we're looking for the shadow of the point P on the plane. Looking at this picture, the orange vector is just going to be the projection of PQ onto N, where Q is any point on the plane. And then the projection of the point P onto the plane will be P plus the orange vector. The formula is that the projection of the point P onto the plane is P plus the projection of PQ onto N. Let's do an example. Find the projection of the point 1, 2, minus 4 onto the plane 2x plus y plus 4z is equal to 2. We need the normal vector to the plane. Straight away we can write down 2i plus j plus 4k. We also need a point Q which lies on the plane. Remember how I said we could always find a point on the plane. We choose two of the numbers to be 0. Let's say we choose y is 0 and we choose z is 0. And then the equation simplifies to 2x is equal to 2 or x is equal to 1. So quickly we could say that the point 1, 0, 0 lies on the plane. We can calculate PQ. We can calculate the projection of PQ onto N. We know how to do projection of a vector onto a vector. And then after we have those, we can do P plus the projection of PQ onto N. And I leave it for you to check that the answer to this question is 7 over 3, 8 over 3, minus 4 over 3. Now, before I go on to the next idea, let's do a quick check that this could be the right answer. Is this point really in the plane? It's possible we've made a mistake in our calculation, so if there's time in the exam and you're given a question like this, it's worth just taking a minute just to do a quick check. I want to check that the point 7 over 3, 8 over 3, minus 4 over 3 really is on the plane 2x plus 4 plus y plus 4z is equal to 2. So what I do is I put 7 over 3 instead of x, I put 8 over 3 instead of y, and I put minus 4 over 3 instead of z. And I add them up, and the question is, do we get 2 or do we get a different number? This time we do get equal to 2. So this point really is on this plane. Probably we didn't make a mistake in this calculation. The next idea is the projection of a line onto a plane. Let's suppose we have a line passing through the point P in the direction V, and let's suppose we have a plane with normal vector n. Then there's 3 cases that we need to consider. Either the line is orthogonal to the plane. I'll try to draw a picture of this. Let's suppose this is the plane. Let's suppose this is the line. And it's orthogonal if we have a 90-degree angle between the line and the plane. Case 2, possibility 2, is that the line is parallel to the plane. As we have a plane, And let's suppose we have a line which is parallel to the plane. That means it doesn't intersect the plane anywhere. And then there's a third possibility. The line is not orthogonal to the plane and it's not parallel to the plane. If it's not parallel to the plane, then it must intersect the plane somehow. And the angle is not 90 degrees. We need to look at these three ideas separately. First, let's think about what we do if we have a line which is orthogonal to the plane. That's the same as saying that the vector n is parallel to the vector n. How can we check if two vectors are parallel? We can calculate their cross product. If their cross product is the zero vector, then we know that they're parallel. This is the easiest case. The projection of the line onto the plane, that means squashing the line down onto the plane, we would just get the point where they intersect. So the projection of the line onto the plane would just be exactly the same as the projection of the point P onto the plane. Or we could do what we did before when we asked where does a line intersect a plane. Case 2, a case where we have a line which is parallel to the plane. We know we have this case when the vector v is orthogonal to the vector n. How can we check if two vectors are orthogonal? We can calculate their dot product. If their dot product is the number 0, then we know that we have orthogonal vectors. I want to project this line onto the plane. So as before, there's two ways to think about this. Either we squash the line down. Imagine putting your hand at the top and pushing downwards and squashing this plane down on this line down onto the plane. We would get the black line in the plane. Or if you want to think of it in terms of shadows, imagine that there's a sun up the top, shining downwards, and we're looking for the shadow of the line onto the plane. We're trying to find the line which I've drawn in black in this picture. Now, the black line and the red line are parallel. They both have parallel vector v. They just pass through a different point. The black line passes through the point projection of P onto the plane. So the projection of the line L onto the plane is going to be the line passing through the point projection of P onto the plane in the direction V. Case 3, a line which is neither parallel to nor orthogonal to the plane. Then this line must intersect the plane at some point, let's say at the point B. The black line, the projection of the line L onto the plane, is going to be the line which passes through the point B and the projection of the point P onto the plane. If we do a question like this, we're trying to find 2 points, B and the projection of P onto the plane, and then we know how to calculate a line passing through 2 points. To finish this lesson, I'm going to do some examples. Find the projection of this line onto this plane. Step 1, find V and N. You know how to do this now. Step 2, does the line intersect the plane? In other words, I'm asking, is the line parallel to the plane? So what we do is we calculate V dot N and we find that we don't get 0. We get a number which is not 0. So the answer is yes. the line does intersect the plane. That means the line is not parallel to the plane. So there's two possibilities. Either the line is orthogonal to the plane, or the line is not orthogonal to the plane. Which one is it? We'll come to that. First, I want to find the point of intersection. So just as we did before, start with the equation for the plane and substitute in the line parametric equations. Replace x by 7 plus 6t, etc. I'll leave this calculation for you to check. You can check that the point of intersection is 9.4, 3, 5.2. Step 4. Is the line orthogonal to the plane? To answer that, we do the cross product of v and n, and I'll leave it for you to check that we get the 0 vector. So the answer is yes, the line is orthogonal to the plane. The picture looks like this, where this angle is 90 degrees, and we've already calculated the point where the line intersects the plane. So now we know the answer to this question. The projection onto the line of the line onto the plane is the point where the line intersects the plane. So this must just be the point 9.4, 3, 5.2. Let's do another example. Find the projection of this line onto this plane. We need to know which of the three cases do we have. Is the line orthogonal to the plane? Is the line parallel to the plane? Or neither? Step 1, find v and n. Here they are. Step 2, does the line intersect the plane? We calculate v dot n and we get 0. The answer is no. The line does not intersect the plane, therefore the line is parallel to the plane. So the picture looks like this. Here's our plane, and here's our line. We're going to squash or project the line down onto the plane, and then we're going to find parametric equations for the new line that's in the plane. We know a vector which is parallel to the line that we want. All we need is to find a point on the new line, to find a point on the projection of L onto the plane. The point 1, 2, 3 lies on the original line, and the point 9, 0, 0 lies on the plane. So we do our calculation. PQ is 8i minus 2j minus 3k. We can project this onto n. Find that we get a half n. And then the projection of P onto the plane is going to be P plus the projection of PQ onto n. 1, 2, 3 plus a half n. We find that that's 5 over 2, 4 minus a half. Let's just do a quick check. Is this point really in the plane? Does it really satisfy the plane equation? Stick these numbers into our plane equation, 3x plus 4y minus 7z, and we get equal to 27. So yes, this point really is on the plane. Looks like we didn't make a mistake. And then the final step is find the projection of the line onto the plane. We know a point on the new line, and we know a vector which is parallel to the new line. So we have enough information. The new line, that's the projection of L onto the plane, must be 5 over 2 plus 40, y is equal to 4 plus 40, z is equal to minus a half plus 40. And then the final example for today's lesson. Find the projection of this line onto this plane. We start by writing down V and N, and then we ask the question, does the line intersect the plane? We calculate V dot N. We get 506, which is not 0. So the answer is yes, the line intersects the plane. The line is not parallel to the plane. Where? Where does the line intersect the plane? We do our calculation, same as before. I'll leave this for you to check. The line intersects the plane when t is equal to -1, so it must intersect the plane at the point 0, 3, 6. Step 4. Is the line orthogonal to the plane? Now, because V cross N is not the 0 vector, the answer is no. The line is not orthogonal to the plane. So now we know what the picture looks like. We know we have our plane. We know that we have our line. And then we know we have our projection of the line onto the plane. We know that the line that we want, the purple line, passes through this point where the line intersects the plane. We know this point. We just need to find another point on the purple line. So step 5, find another point on the projection of the line onto the plane. We have the point 15 minus 12, 17 on the original line. I'm going to project this point down onto the plane. Just as you did before. Just as we did before, we can do the calculation. P plus the projection of PB onto N. And we find that the point 2 minus 3, 1 is on the new line. And then we're almost finished. To finish, we need to find equations for the new line which is in the plane, for the shadow of the original line or the projection of the original line onto the plane. We know 2 points on the new line. Using those, we can find a vector which is parallel to the new line. And then the answer is we want the line passing through the point 0, 3, 6 in the direction of this vector. So the answer to this question is x is equal to 2t, y is equal to 3 minus 6t, and z is equal to 6 minus 5t. I'm aware that projections are quite difficult. That's the end of our topics on geometry of space. Next week, we're going to start talking about a different type of mathematics. We're going to start talking about combinatorics and probability. Combinatorics is a fancy way of saying counting. Next week, we will talk about chapters 17, 18, and 19. Do you have any questions?